Today we're going to take a look at Hess's law. Okay, so Hess's law is going to allow us to find some more delta H's for reactions in a slightly different way. So one thing we need to learn about or know before we can look at Hess's law is that enthalpy is a state function. Okay, a state function. And what a state function means, it's not path dependent. Okay, not path dependent. So in other words, it doesn't matter how you get there. Okay, all it cares about is where you start and where you end. Okay, one option, maybe one time you're going to go up, back down, and then there. Or maybe another time you might just go up and down. Okay, both of those start and end in the same place. Now, they don't get there the same way, but that's a state function. Hey, where am I starting and where am I ending? And how I get there, it doesn't really matter. Okay? So enthalpy is not a path dependent because it's a state function, right? So what does this mean for Hess's law? Okay, Hess's law tells us that reactions can be thought of or looked at as a sum of multiple reactions. Okay, so one overall reaction can be looked at in a sum of multiple different reactions or a steps. So reactions might not just happen in one step, but you can look at them as multiple different steps, okay, or a series of steps that takes place. So let's take a look at an example. What does this actually mean? Okay, so let's see we have this reaction. Okay, nitrogen gas plus 2 moles of oxygen gas goes to 2 moles of NO2 gas. Okay, so this reaction is studied, and the delta H for this, and we're going to label this as delta H1. So our first delta H we're going to look at is at 68 kilojoules. Okay, 68 kilojoules for that. For 1 mole of this, 2 moles of oxygen, 2 moles of nitrogen monoxide. All right. First off, delta H is positive here. So that means, is it endothermic or exothermic? It'd be endo. A positive delta H means it's endothermic. Okay. So another way to look at this reaction would be this, a series of 2 steps. So let's say before nitrogen reacts with 2 moles of oxygen to create nitrogen dioxide, what if this happens first? We have nitrogen reacts with a mole of oxygen to produce 2 moles of nitrogen monoxide. Okay, so this is reaction 1, and let's say this has a delta H. We'll call this one 2, and let's say that's equal to 180 kilojoules. But then we also know that when 2 moles of nitrogen monoxide interact with a mole of oxygen gas, they react together to produce 2 moles of NO2. Let's call this delta H3. And let's say the change in enthalpy for this is a negative 112 kilojoules. All right. So what does this do for us? I'm going to face over this so you can see all the numbers. Okay. So Hess's law says I can look at an overall reaction as a series of multiple steps of reactions. So let's add these reactions together. So let's see what we have here. So we have nitrogen as a reactant, and we have no nitrogen by itself as a product. So it's going to come down to my final overall reaction. Okay, I've got a mole of oxygen here. I have no moles as products, so I've got another mole of oxygen as a reactant, so that's going to use 2 moles of O2. Okay? Then I've got 2 moles of nitrogen monoxide as a product, but in this second reaction, I use 2 moles of nitrogen monoxide as a reactant, so those actually cancel out. My net change is 0 because I produced 2 moles of nitrogen monoxide, and in the next reaction, I consume 2 moles of nitrogen monoxide. All right? So I've used nitrogen, I've used my 2 moles of oxygen. Goes to, well, what's left? 2 moles of nitrogen dioxide. Well, this reaction is the same as this reaction. Okay? So this reaction can be looked at as a series of steps or sum of these 2 individual reactions. Right? So graphically, what we might look at their delta H's, it might be something like this. Okay? So we have 180, and then, so for the first reaction, we have reactants. So this is N2 and O2. Okay? And they go up. It's endothermic, so I have to put energy in. And it goes up to 2 NOs. Right? Well, but then, we're at this energy state down here, we got 2 NOs plus O2 reacts, and it drops back down here. So this is a positive 180. It's a negative 112. Well, I start here and I finish here. Okay? So since enthalpy is a state function or not path dependent, all I need to know is, well, what's this? This is my delta H for my overall reaction. So I'm going to sum these together. 180 minus 112 is 68 kilojoules. Well, what do we find or say the reaction delta H for this overall reaction was? Well, it's 68 kilojoules. So whether you look at the reaction as a single-step reaction or a multi-step reaction, we still get the same change in enthalpy. Okay? So let's look at another reaction here. I want to know how much energy does it take, okay, what's my change in enthalpy, when carbon goes from graphite to carbon diamond. Sorry, I didn't mean to write solid there. Carbon diamond. Thinking about opening up my own jewelry shop, and I want to start, buying some graphite and making it into diamond. I want to see, okay, well, what's my change in enthalpy for this? Okay? And that's kind of a hard reaction to study. But we've done some other stuff. We have carbon graphite. I'm just going to put G for graphite in the solid form. And I've combusted it, or people have combusted it with oxygen, with O2, to create carbon dioxide gas. Okay, so that reaction is studied. And the delta H for this is equal to negative 394. Whoa. (394 kilojoules). Okay. And we also know that carbon diamond, solid, plus O2, so we can combust it, goes to carbon dioxide. And the delta H for this is equal to negative 396 kilojoules. Okay, so I have these 2 other reactions, and Hess's law tells me that this overall reaction can be thought of as a series of steps. Okay, so let's look at what we got here. I have carbon graphite as a reactant, and I have carbon solid diamond as a product. I've got carbon graphite as a reactant down here, but carbon diamond is a solid is a reactant down here. So I'm going to flip this second equation here. So I'm going to have CO2 decomposes into carbon diamond, solid, plus O2 gas. Okay, so I flipped that one, so I'm going to cross that out. Now, if I flip the reaction, if we think of delta H's, if that's my delta H, sorry, it was endothermic. Let me draw it. No, it's exothermic. Let me draw it correctly. So if my original reaction was for the combustion of diamond was like that, and I flip it, well, then what do I do from the delta H? Now I'm starting here and going up here. So all I'm going to do is I'm going to flip the sign. So my delta H for this second equation is now a positive 396 joules. All right, so let's add up these equations and let's see if we get our overall reaction. Okay, carbon graphite. I don't see any other carbon graphite, so that's going to stay there. Okay, oxygen gas as a reactant, oxygen gas as a product. So 1 mole and 1 mole, so my net change is 0, so that doesn't change anything. Okay, carbon dioxide as a reactant, 1 mole, carbon dioxide as a product. So I'm producing a mole of carbon dioxide, but I'm using a mole of carbon dioxide, so that net change is nothing. Goes to carbon diamond. Okay, does this reaction match this reaction? Yes. So if that matches, so we use 2 different reactions to get our initial reaction. Hess's law states I can just add up my delta H's. So my change in enthalpy for this reaction would equal 2 kilojoules. All right, so Hess's law. A single reaction can be viewed as a sum of reactions. And the sum of the change in enthalpy is equal to the sum of the changes in enthalpy for each individual reaction. Things to remember. If you flip a reaction, you must change the sign on delta H. Okay, that's important. Okay. And also, when you're adding reactions up, so this is critical. Sorry, let me give you guys a second to write that. If you flip a reaction, you must change the sign on delta H. Okay. And if something is produced, when you're adding reactions up, if you have something produced in the same chemical as a reactant, they cancel out, because again, our net change is nothing. Okay? All right. Why can we do all this? Enthalpy is a state function. It is not path dependent. So as long as I start and end where I want to, how I get there doesn't matter.